Okay, well, it's a great pleasure for me to welcome today Elaine from the University of Southern California. She's originally from Singapore. She did her undergraduate work at Stanford and her PhD at MIT in operations research, where she was also an affiliated artist in music since she's a concert pianist, as well as being an applied mathematician. She works on the analogs of most of the problems that we work on, except we're doing it in language and she's doing it in music. So in the case of synthesis, she's worked on expressive music synthesis. For music analysis, I think today she'll be talking about pitch structure, which is to say key finding and tonality. But she's also worked, for example, on separating apart the voices in polyphonic music, which is basically a source separation problem done entirely with the language model with no acoustics, since the input to this was MIDI files, I think. Is that right? Yeah. And she's also worked on the more engineering kinds of tasks in music, in particular music IR. There's a whole area of music IR which we've heard about before, those people who are at CLSP year-round, which is queried by humming. So you hum into a microphone and it tries to pull up the tune that best matches you. And in order to do this right, as you can imagine, it helps to know something about music cognition, because most people don't really remember the music really well. Or they're not very good at singing, or both. So you want to be able to do some kind of nearest match which takes into account a complicated noisy channel model of how the music actually comes out of somebody's imperfect manner. So I've talked long enough. I'm looking forward to this and also to the visualizations and also to understanding more about how the techniques that we use do and don't line up with the techniques that people in computational music use. So let's give a hearty welcome to Elaine Chu. Oh, I'm sorry. I forgot one very important thing, which is that she just received the Presidential Early Career Award for Scientists and Engineers, which is, I think, the highest honor that the NSF gives, in that the White House is also in on it. Here's your hat.
Okay. Thank you very much. Without offending anyone, I'll put this on later, so I'm good. Okay. Thank you, Jason. That was an excellent introduction. I gave some thought, actually quite a bit of thought about what I could talk about to a group of people who work on language models. And I wasn't quite sure. So these are some things I thought would be interesting to you, and that might have parallels in the kind of work that you do. So today I thought I'd give a quick overview on what is music engineering research, who does this research, where you can find more material on this research. I'm going to introduce the phantom, and you'll see what it is later, and talk about some models for tonality and tracking context in music. And I think here you're interested in what are some of the unsolved problems. So I put a slide in there of what I could think about would be interesting problems that could be of interest to you, or might have parallels in language. Maybe you could give me ideas on how to approach them. So here we go. So music engineering research occurs across the world in many countries. Some of the research centers are represented here. Oh. We'll need the sound in a bit, but not right now. Okay, that's IRCAM in Paris. This is the Institute for Research and Coordination in Acoustics and Music. And there are various research centers, groups in London. There's McGill that has recently hired quite a few people from these other centers. And there's Berkeley and Stanford have these centers. And there's also several individual researchers or pairs of researchers across between these places that are not represented. I'm just putting up here some of the larger research centers. Here are some of the journals where you can browse and find out more about research in this area. I'm just putting it up there. Yes, there are other people doing this work. And some of the problems have already been mentioned by Jason in the introduction. So I'm going to talk mostly about this part modeling of music cognition today. And problems in modeling of music cognition include key finding, and I'll explain what all that is. Meter induction is how you group beats, time structures, and segmentation for both of them. There's music information retrieval. Jason gave a great introduction on that, and you've probably heard more from Brian Pardo earlier in the year. Collaborative performance is when people play together, more than one person plays together in an ensemble. And these bring about issues of communication, how people coordinate and try to tell the same story. And computer-assisted composition, composers use computer tools to generate music, and expression synthesis, which has parallels in speech. Today I'm going to talk about key finding and segmentation and how it relates briefly to expression synthesis. An example of other people who have done work in this are some of the people represented here. These titles give you an idea of the kind of work that's going on. And this was part of two special sessions I organized back in January. This was in Maryland, in Annapolis. Okay, so before I talk about how we model music cognition, I'm going to show you how you actually perceive music. And we're going to start by looking at the phantom. Okay, so the phantom, who's a fan of this? Who's heard this? Oh, good. Many people. I wasn't sure. I asked for a keyboard to play on, but then I guess it was hard to get one from Peabody, and so last night I went on iTunes and bought it. So this was this is really convenient today. All right, so this is the piece that we're going to look at. Oh, sound. Yes. Mm-hmm.
Is it what good volume?
Yeah. Whoa, yeah. Okay. All right, so what do you notice when you listen to music? Volunteers? What did you hear? Nothing?
Well, there was something.
Okay.
There were these like a gentle change of the note, I suppose.
The note changes, flow. So of the notes, there were some that were more important than others. You heard a melody, maybe? Yes? Yeah? The person singing was carrying a melody.
There were these repetitions.
There were repetitions, there were sections, right? How many were there? You want to hear that again?
Okay.
Introduction. First phrase. Repeat, yeah. Something different. Coming back, but not quite the same, but similar to the beginning. Okay, so you certainly heard some structure and pitch structures at different levels. You heard melodies, which are these streams, horizontal structures, and you also heard when sections changed, right? So I'm going to show you what you heard. Whoa. Never.
On mute in and out, like maybe
Oh, is there an instant mute?
on the keyboard.
Right next to the volume.
At the top.
Yes, okay, I see it. Okay, so you heard the melody. This is the score as you can buy from any store that gives you the sheet music for the Phantom of the Opera. And you have the melody on top, you can have some introduction in the beginning, and you have this accompaniment that goes with the melody. And in the melody, I'd like you to hear whether or not the melody is ended. Let's go back and hear it a third time. Oh. Mm-hmm. Is it finished? No, you'll be very dissatisfied if I stopped right there. Okay, let's hear the continuation. Ended? We've had 2 repetitions. No, you want more, right? Okay. If I stop here, really bad, right? Okay, now we'll hear more. Is that good? That's a satisfying ending, right? Okay, so you've told me what you think the key is. It ended on the key, and you said, well, I'd be satisfied with that. So that means that with this melody, you waited till this point to say, okay, I'm happy now. Everything's peachy. Okay? All right, so that note where it ended right there, where I stopped the melody, is the key. That is the most important, most stable pitch of all that you've heard before that. Okay? And the way the melody is arranged is such that it makes you want that note to be the ending one and the most stable one. So that's called key finding. So we're trying to build computational models that will predict what this key is. Well, predict's not quite the right word. We're not trying to predict before people will know it. We're just trying to mimic what people can do. Okay? Another thing is, what you heard was, you heard the melody the first time. Oh, wait, the introduction. So this is the introduction before the melody comes in. So that's the melody the first time. It's in the key which you are expecting at the end. And you heard it a second time, also in the key that you're expecting at the end. But in the middle, something changes because it actually changes mode. It could be a different key. So it's kind of a little cloud. And finally, the key comes back again, restated, and you're very satisfied. We've come back home. Okay? And so this is where we end that statement, the final statement.
Does key mean what one normally means, namely key in C minor or
yes.
something?
Yeah.
And so to speak, this is the
This is C. Oh, this is
well, whatever it is.
the main note in the key. Yeah.
I see.
Right. If you're in C minor, this is C. If you're in D major, this is D. And so far, everything is basically in D. And it went away into B minor and came back to D. So that's what it's done, and that's why music is interesting, because we're following this. We notice it even though we might not be able to call it a name. So we notice these kinds of changes. And finally,
Modern composers have it too.
oh yes,
I mean, I know
yes.
he's sort of modern. but
He is sort of modern, but he uses traditional techniques. Yeah. No, yes, modern composers use this too.
Roren.
Yeah, this is, I'm not familiar with Rorem's output, so I can't say,
I see.
but many of them do. And something goes on. When the orchestra comes in, Andrew Lloyd Webber was chosen because he has many examples of these kinds of things. It's kind of like going to Las Vegas. We have all the sights in one place. Okay, so these are all the sights in one place. So at this point, he actually changes key again when the orchestra comes in. To crank it up a notch, he shifts everything up by a half step. Okay, and so this is the sunny next key. Okay, so this is a much stronger feel. So this is how he creates interest in this particular piece.
And the point you're making, I guess, is that this is more general than any composer, that any music that didn't end in the main key would not sound pleasing to people.
Yes. Pitch-based music. This music that's purely rhythmic, in which case you're not looking out for pitch. Yeah. Mm-hmm.
There's also music that's deliberately designed to be unsatisfying.
Right, that too, to be perverse, yeah. Okay,
So Karam,
yes.
for instance, would have this too.
Crumb.
Crumb.
The thing is, even modern composers have to work within this context because this is how we are this is what we are expecting. This is what we've been either conditioned to expect, or is there something innate in the ear that wants to hear this? But that's debatable, so I'm not going there. But for yeah.
So while we're on this line of questioning, let me just ask quickly: is the ambition to just are the keys that you're looking at things like D minor, or are you trying to distinguish the different minor modes?
The different minor.
In other words, is your output D minor or D Dorian?
No, we haven't worked on different minor modes.
Okay,
yeah,
right.
so just
basically
D minor.
4 keys that you can output.
Yeah, right.
Yeah. Okay.
Okay, so given that I've shown you what you're looking for in key, now I'm going to show you a computational model. Actually, I'm going to build up to it. So I'm going to show you a few computational models for doing it. Okay, so Roger Shepard was trying to model pitch relations because a melody is basically a stream of pitches with different durations. And he determined that any cognitive representation of musical pitch must have some properties such as regularity, symmetry, and transformational invariance. Because C major and G major is just 5 notes apart, and they're basically the same. You just translate everything 5 steps up, right? So based on, I didn't show here, but you can get books where Shepard has come up with numerous models, geometric models for musical pitch, where he tries to explore different relationships, how close pitches are, how distant they are. But I'm going to talk about one particular model that Longan-Higgins proposed, and this was back in the 60s. And this is called the harmonic network. And these are the names of pitches. So typically A in the middle of the keyboard is 440 hertz, and but it could be 443 for certain orchestras. But we're not going to worry about the exact frequency of these pitches. We'll just call them pitch names. Okay, A, whatever you call an A, that's an A. Everything else is relative from it. Okay. So in this representation, things that are next to each other, so the C and this G, so C, D, E, F, G is 5 scale steps apart. That's a frequency relationship of 2 to 3, okay? And that's 2 to 3. And then you have vertically what is called a major third, and that's a frequency relationship of 4 to 5, 4 to 5. And you have octaves, which are doublings of frequencies. And so you have this 3-dimensional grid that represents all the pitches that you can find notated in most scores. And this representation is useful because it clusters meaningful relationships, things that are nice fractions of each other. Okay, frequencies that are nice fractions of each other. And together with Steedman, Longet-Higgins came up with a way of using this grid, well, just one sheet of the grid. You can compress all of them together, flatten all of it, and get this one single sheet, and looked at it and found that things that are in the same key are nicely compact and clustered on this grid.
What do you mean the same key? I thought these are the keys.
No, these are the pitches. The notes in the notes in the key.
Uh-huh.
And so the C, D, E, F, G, A, B. So do, re, mi, fa, sol, la, ti in the key of C major. So that's do, re, mi, fa, sol, la, ti. If you map them on this grid, you get them in this nice L shape. And the same, so any major key maps to this nice shape. That's another major key. That's the key of A flat. That's E flat, and that's G. So you just shift it around, and it's all, they're all major keys. And the nice thing is that minor keys, right? Minor keys also exist, also form nice shapes. They're also compact. You can draw this nice boundary outline around it, and you get this is A minor.
Is this restricted to Western music, or is this what you're telling us universal?
This is Western music for now, yes. But if you look at pentatonic music, they're often a smaller shape that's also compact, yeah. So for example, this Bach melody, da da dum bum ba da da dum bum ba da da dum ba da 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 da. Excuse me. So this is C minor, and I don't have perfect pitch, so just since it's you can translate it anywhere. The melody is the same, whatever key you sing it in. So here it is. Okay. So the method that they used was basically, well, if you can map all those pitches into one of these shapes, then it's in that key, right? So if you have, first you hear a C, and then you look at your grid and you go, well, here's C, it could be that shape, but it could be that other one. Could be that, or that, or that, or that. Okay, could be any of these, right? And I didn't put even the red shapes on, just to make it easier to explain. Okay, then you hear the B, right? You can eliminate quite a few of those when you hear the B. And when you hear the C again, you don't really do anything, but you don't get more information. And then you hear the G, and you're down to just a few. And then you hear the A flat, and you're down to only one. So that's the key. So this is the method for determining key, and they came up with this in 1971. Yes?
So what would it do, though, if in that context there was, in that same key, there was the B flat and the A natural? So in C minor, you can have...
Right, this is the harmonic minor. You're talking about the melodic minor?
Okay.
Yes, there are other minors, but they only, in their tests, they only use the harmonic minor shape. Yes. So that, you pointed out one problem there. If there are pitches that are outside of the designated shape, then it's not going to find the correct key. So it's not robust to errors or to noise.
Or what?
I mean, it's not just noise. It's noise from the point of view of the model, right? The model doesn't handle passing tones.
Yeah, it doesn't handle passing tones. That's right. Mm-hmm. Yeah.
I mean, it's not noise in the sense of, I mean...
Oh, no, it's not bad sounds. It's just that it doesn't fit in the particular key shape. Yes?
So how's this just different from, I imagine, before this research? I mean, people were already aware of the scales, and they could just told you, you know, when this, if you had a list of all the scales and all the pitch notes in them, then you're just doing a search to say, you know, which list matches up to the notes you see. I don't understand how...
Well, this...
Is the point that you don't need this geometric grid layout
Correct.
Yes.
in order to run this algorithm?
Right. You can certainly match to a profile, right? A a histogram of what pitches are present. How is this different? I'm not quite sure.
Well, you might use the geometry of the grid to do smoothing if you don't have very much.
Yeah, but we're getting to that. Yes, but in this particular state, I'm not quite sure how much advantage that gives you above just searching for the correct set instead of the shape. Yeah.
Nonetheless, it's a bag of pitches model.
Yes, exactly, unordered bag of pitches. Yeah. Oh, this has been implemented. You can download it and play with it in my class. So one of the students, Daniel Han, did it. Okay, so another model that came out of the psychology field is by Carol Krumhansel. And she came up with a very systematic methodology of determining how well tones fit in keys. So she would play, so the experimental design is like this. She would play something that generates a context. So you hear that and you get inducted into that context. And then a single tone will be sounded, and you're to then rate this tone, right? This is a context that's generated. Some tone is sounded, and you're going to say it fits, it doesn't fit, or on a scale to 1 to 7, how well it fits, or how, out of 1 to 7. Or it doesn't fit on a scale of 1 to 7. And so she created these profiles of how well different tones, the do, re, mi, fa, sol, la, tis, in a scale fit in that context, in that key. So these are the profiles. These are sort of the average ratings of all the users of how well different tones fit in a context. And so when you get, this is kind of like the templates from the previous method. So when you get a melody like this, again, you would get C, and you start with an input vector, so all you have is C, which is 1. And then you match it to these templates and go, well, which of the key templates does it fit best? And then you hear a second pitch, and so it's split now between C and B. And now you again compare it, get the correlation coefficient calculated for all the different templates, and keep going until you get the key. All right, so this is the other method, and it's based on these probe tone profiles. And these were derived from listeners' ratings. Okay. So now we're going to transition into the smoothing effect that was mentioned earlier by Jason. And if you take a look at this grid that nicely clusters important relationships, this is Long-Higgins harmonic network. You'll see that there's a D, and D is repeated again. And therefore, you can actually roll this whole thing up. If you have a sheet of paper, print this grid out, take the two, roll them together, and you'll see that it's actually a spiral. So the spiral shape is inherent in this representation. It's just a two-dimensional representation of this spiral. Okay, so if we look at the spiral, this is where we're going to begin the smoothing process. So this was the model that I proposed back in 2000 in my dissertation. If you look at a three-dimensional structure, what you can do is use its interior, right? We are now in 3D. And we have an interior to work with. So as before, I didn't mention this, but apart from the fact that keys are nicely clustered, the triads that, any of you play guitar? When you play chords, you're basically playing bunches of chords that are related by thirds. And 3-note chords are called triads. And the 3-note chords map to these nice triangles, again, very nice compact shapes. So that's a major triad. Another major triad, another one, and another one. So you have all the major triads that line up nicely, and you don't really have to represent them as triangles. As some music theorists do, they actually look at how triangles flip on that grid to map out triadic motion. So you can actually represent each triangle by a summary point that's in the center of the triangle. Since they don't overlap, it really doesn't matter where on the triangle it is. But you can try to be nice and make it closer to its root, and not so far from the fifth, and maybe more distant from the third. And so that's the nice mathematical equation that describes the triangles, the points representing the triangles. And 3 adjacent triangles will give you the 3 chords, the 3 triads that define a key. So typically these are called the 1, the 5, and the 4 chords within a key. So this is the key, if this is C. So this gives you all the pitches, these 3 triads gives you all the pitches in that key. And so if you rotate them, you get all the major keys. So you can then represent these keys as the summary points on these triangles.
When you say adjacent triangles, in what sense are they adjacent? Do they share a vertex, or they, in some Euclidean sense
They share a vertex, yes.
So you're going up the spiral, let's say, and you
Yes,
take one triangle,
right.
take the one triangle,
Next
share
one.
the vertex with it,
Yeah,
go up
and the
again.
next, yes. And they are also related by fifths because of the original grid. Okay, so the nice thing with this 3-dimensional model is that we still preserve that compact shape of the things that belong to the same key. And so what used to be this L shape now becomes this thing over here, and you have this nice volume that's compact that contains all the pitches in that key but no others. And so you have the shape representing a key, and you can generate a center representing that key that has all those pitches.
You said there is some kind of a geometric mean?
Yes, some geometric mean, but it's designed, you can put constraints on it for where you want it to be closer. So if we go back to the melody that we were listening to, da 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 da. So that's what's over there. So if you take that melody and you generate a center of effect for that stream, and you get this green thing over here, then you can then look at the inner spiral of the key representations and match it to the closest one. And this nearest neighbor search would give you the key. Yes?
I can't quite see your formula from here. When you compute the position for the snippet of music,
Yes.
do you weight by the length?
By duration.
Okay.
Yes. So if you take the first note, you would start over here. Let's say the first note is here. And then you hear the second note. Then you have the average of the two since they are of the same duration. And then you hear the third one. So it goes like this. Da da da. Da 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 da. Okay? So this is what would happen if you did this with a computer. And you would get this green blob in the center that represents the center of effect of this melody.
And it's the point that where you segmented it in the wrong way to tease us about it, is the point that at that moment the green ball is quite far away from the red one.
At this moment,
Yeah, I don't know, you played it and you said, now this is unsatisfactory, this is unsatisfactory, etc.
yes,
Yeah,
it's
when
the
you
distance to
the
the
distance
particular
of-
within
Is
this.
that computation? If I computed it by this formula, the way the ball was traveling,
Yes,
so the point where you hypothesize that there might be a ending when you knew it wasn't,
right.
that is a point at which the green ball is far away from the
From the center of the
From the
melody
center.
center.
From the red ball.
from the red ball.
No, it actually is not.
It's a
That is a point where the current note in the melody on a strong beat at the end of a phrase that is symmetric, I mean, there's many conditions, actually is the note that's the closest red thing. Yeah, so that's what that is. But there are many conditions for determining how we, to model computationally how we perceive where the key is. Yeah.
I have a question.
Yes.
So as you showed, often, for example, in Western music, keys might come in 4 measure clusters, for example. So you showed that the third cluster for Think of Me switched to a B minor. So my question is, when you're calculating these, obviously you don't want to count all of the notes in the entire song. You only want the most recent few measures. So do you have some window that you look at specifically?
We're coming to that. But first we're looking at the most primitive model, which is just accumulating information. Okay, so and then you compare it and you get the closest key. All right. Of course, this doesn't just apply to single melodies. You can also apply this to anything that's a bunches of notes over time. Because you can, the more the merrier, the more notes you have, the more information you have, and actually the easier it gets to predict the key. Okay, so this was tested on Bach's Well-Tempered Clavier, Book 1, all his fugue subjects. And the nice thing about using this test set is that there's 1 in every key. He was very systematic about it. And it really doesn't matter what key the piece is in. So if you're actually doing testing of key finding algorithms, it doesn't matter what you test. You could put everything into the key of C if you wanted, and it wouldn't change the difficulty. Yes?
One thing I was thinking about is that once you have this continuous representation, I don't know what Jason called them, passing notes or something.
There are accidentals.
Yes.
So those would they fit nicely because they would really be in between?
They would perturb the trajectory, but only by a little bit. They wouldn't, it would still be.
Would they be in between the 2 notes that you're transitioning between, the 2 pitches that you're doing?
They could be very distant.
So they could be.
Yes, they could be very distant, but the thing is, these things tend to be of short duration, and they don't change the context very much.
Right. So this is actually interesting. If you really wanted to model accidentals, or in particular passing tones, then it seems like those should be handled by looking at the closeness of pitch rather than the closeness of the spiral array.
Exactly.
And so you'd want your model to recognize that there are 2 different kinds of things going on.
Yes, that would be closeness according to frequency rather than according to this geometric model. Yes. Yeah. So just quickly, I tested it on the original shape matching algorithm and the probe tone profile method, and this is the CEG method. And on average, it took much fewer notes to get the key, basically 3.75 versus 5.25 and 8.71. And notice that we're looking at single melodies, which is very little information. And the places where it gets it really, really wrong, like 16 steps, the whole thing, and the dagger there really means that it didn't get the answer at all, are examples where in a grid, there are 2 different keys that were possible for all of the notes, but we didn't have enough information to distinguish between the 2. Okay, so just quickly, the probe tone profile method, which is this, the one where you calculate correlations, and the spiral array method, the center of effect, both tolerate ambiguity and notes that are not inside the key. Okay, but all 3 ignore any note order. It's just this unordered bag of notes. So we actually have to determine how big of a window we're going to look at. So, for example, notes, this is extraneous to the window idea, but in general, notes on strong beats are more important, so we actually need some model for the metrical structure. And the order can actually change the context. So notes in one order do not generate necessarily the same context if you change its order. Okay, so I've shown you how you actually recognize a key. So given that you can recognize a key, how can you track it over time, right? So we have to have some kind of a window. So one of the projects that I've done, this is joint work with Alex Francois, is the MuseArt project, Music on the Spiral Array Real Time. So this is Musa RT. This is a project where we had all the algorithms using the spiral array implemented in a real-time application so that you can see the trajectory as it develops over time. And you could see the keys and the chords, the closest keys, the closest chords. And there was both a long-term and a short-term center of effect. And these were simply every incoming event was multiplied by some alpha, and anything before that was multiplied by 1 minus alpha. So it was integrated over time. And so the key was the closest key to the current long-term CE, and the chord was the closest triad to the current short-term CE. Okay? So if you look at this picture, what's showing is a local CE, the green blob. The closest triad will light up. There's a triad label, it turns red. So that would be A, I think. And then there's a long-term CE. And then the closest key is shown as this blob in the center. It pulses. And the size of the pulsation gives how close you are, is inversely proportional to the distance to the current CE. So the closer you are, the bigger the blob. And it is labeled over here. So the closest key is also labeled. So how this was designed was using Alex Francois' software architecture for immersive presence, because if you ever try to implement any of these things and try to get it to run in real time, it actually doesn't work if you do it a naive approach in Java or C++. So this was done in a more structured way, where we had the spiral array and its structures shared amongst different streams, different processing units. And the MIDI event came in from a performer and went through the system as a MIDI stream. There are 4 separate streams being managed here. And the real-time CE algorithms were being calculated in parallel and rendered, so the structures that were identified were rendered in real time. And the camera control, someone could fly through this thing. It's a 3D space after all, so there's a camera control, and you can zoom in, zoom out, and go around and look at structures as you wish. And so that's the tonal analysis unit and the interactive control unit. And the spectator can actually look at these things as it's happening. So at this point, I'll show you some videos. So this is an example. How many of you know Pachelbel's canon? Oh, good. I got this from iTunes too. This was in the top 10 classical downloads. So this is, but this is a MIDI version of it. Let's see. It's kind of blur, is that okay? Yeah. This is autopilot, so nobody's driving. So you can see it's outlining the same chord patterns over and over and over again. There's more information coming in. So there's more threads that are coming in, and the line gets more jagged, as it's not as clean as before. But it's still basically tracing the same basic path over and over again. Okay, I won't make you listen to all of it. Yes.
So this is a piece of music with multiple voices.
Yes.
Do they all play in equally, or do you just take the top, or
No, everything.
everything just...
Yeah, just take all the notes. You
So
can.
there'd be an extra weight given to it?
I don't think so. Maybe the bottom.
oh,
Because
sorry,
usually,
maybe
yes,
bottom.
yeah.
Okay. Maybe both. I mean, if you have jazz piano, there are a lot
Right.
of color tones in that are not included.
Yeah, it
Sorry.
depends on the music, really.
Yeah,
Yes.
okay.
Yeah. This is another example, just quickly. This is Bach, the cello suite. A very different trajectory. So it's in the key of G, and the triads are flipping around. Okay, and quickly, we don't just look at very old music. Yes?
What does the blue triangle mean?
Pardon?
The blue triangle?
The blue triangle, okay, they're the minor triads. So the red triangles are the major triads, and we made them blue for the minor.
So it went briefly into E minor, but I didn't see the pulsating or move. Is that because you weren't windowing?
Yes, that's the other thing. Because this is a constant factor, alpha, that determines how much.
The decay factor?
The decay factor.
Yeah, okay.
Yes. So you actually have to change the decay factor to actually catch everything that's happening in the music that we are able to catch.
Or you could try to integrate segmentation.
Yes,
with it.
exactly.
Yeah.
Right, but then it won't be as real time as, well, it gets a little more complicated.
Sure.
Yes. So this is Barber. So it travels much larger distances. So this is one of those pieces that's in the key of B flat minor, but never uses that triad except for brief 2 seconds in the middle. But it uses everything around it, so you can actually get the key. Okay. So all of these are, I've put these online. You can find them. You can download and look at these videos. Okay. Watching the time. Okay, so now we're moving on to, now we can track context, and you've heard about some of the problems of tracking context. How can we segment? I'm going to again introduce a very rudimentary algorithm. You can, of course, make it more complicated, and, but the ideas are basically the same. So instead of trying to find key, this is the center of effect of a bunch of notes you've heard, okay? And we know that this develops and gets close to the key. So why bother finding the key if this represents the context and we're only concerned with segmentation? We can actually use this center of effect as a proxy for the key context, right? So for this context that's we're sort of noodling around. And why bother about key context when we can just deal with any kind of context in modern music where people don't use the regular keys anymore? So let's say we have a different context, this other context. And we can compare the two by measuring how distant the centers are. So this is the basic idea of how to segment between different contexts. Okay? So if you have a green context followed by a yellow context followed by a green context in a piece of music, like up there, then at the boundary between the green and the yellow context, if you're measuring the CE of that and the CE of this and the distance between them, this distance is going to peak at the boundary when all the notes on one side is from one context and the notes from the other side is from a different one. So you can basically slide these two windows across and see where the peaks occur, right? So you can go, oh, it changes context, so there's a peak at that boundary. There's no peak at this point. There's another maximum over there, and no peak. And this is the basic idea of real-time segmentation. Just slide this window across. Okay.
And you want to segment it at what boundaries?
Context boundaries. So they could be key changes in the larger context.
I'm sorry, the y-axis here is?
Distance between the CEs of the front and back. So before and after. So if you're here, before, after, you segment at that point if there's a high peak. between the distance of the before and after context.
And within that window, it's still a bag of
Yes,
pitches,
unordered
but-
pitches
But the temporal part comes from the fact
come from the
that-
fact that you're sliding.
And you
yeah.
still have this alpha decay or not?
In this particular implementation, no. Yeah.
Yeah, so there's actually roughly the same algorithm in Jeff Renner's PhD thesis for text segmentation.
Oh, I didn't know about that. Yeah.
Actually, it was, I'm sorry. It's Marty Hurst's algorithm. It was earlier than that. Renner improved it by looking at boundary features.
I'd like to get that reference.
sure.
Yeah. Mhm. Okay, so a quick example. This is Schubert. Schubert's famous for doing these drastic key changes. And this is an example where he writes it in. Okay, it goes from 4 flats that are these symbols to 4 sharps. So the keys are indicated by these key signatures. And you see numerous points where he goes from 4 flats to 4 sharps, and then 4 sharps to 4 flats, 4 flats to 4 sharps, and so on. So I've marked them by these red lines. So if you did exactly what I showed earlier and did the sliding window across, what you're going to see, this is the data output, these kinds of peaks. Okay, the distance is going to be very distant. And this is a very extreme example. It's a very clean, clear example. And this is for a window of 9/8 notes. This is for a window of 18/8 notes. And you can still see the peaks. So the difference between the 9 and 18/8 note windows, one's smaller, one's larger, is that you get a lot more of these local patterns with a smaller window, and you get a smoother pattern with a larger window. Okay. Another example, over here, this is a more subtle change, but that's basically a different region over here. This is similar to the Andrew Lloyd Webber example, where he goes in one key and then goes to a different region and then comes back. And again, you still get to see that kind of peak, but it's not as pronounced. And here's another window. Okay, so I'm sure you're all dying to see what happens when you do this to Andrew Lloyd Webber, right? Okay.
Before we go on, I have a more general question. So instead of having a window, why not have a generic?
Yeah, a wave, yes, right, a decay outward
and
from
let
it.
go wherever it estimates?
That would be fun to try, yeah. Yes.
I would be worried about off by 1 note errors for this kind of thing.
Oh, there are many off by 1 note errors.
Yeah.
Yeah. But, you know, it's much better than before where there's no boundaries. But yes, you're right. But off by 1 note errors are actually very hard to change because some of them are due to phrase boundaries, gestures that are not actually context-based. They're based on symmetry, things that you perceive on a different level other than the context.
Well, if what you mean is you'd like to be able to say that the boundaries occur at the bars between measures, for example.
Well,
So you'd like to do meter at the same time as a preprocess?
Well, you need some metric boundaries so you can set up a grid, so you can snap to grid when you get an answer.
Yes, I understand.
Yes, so that's one way of doing it. But for example, if this is the boundary that a person, a human being perceives, and the notes to the right of the boundary also belong to the context before, then it's really hard for a machine to determine where the boundary is without other structural information.
Yeah, that's certainly true.
Yes.
I'm sorry. The case that I was thinking of was where your decision between putting it here and here, if you looked at a very narrow window, you would be sure to put it here. But because your window is wider, the fact that you have an F sharp over here far away is influencing this.
Determining the window size is actually non-trivial. I'm not quite sure how to do it yet.
Yeah,
So I just tried a whole bunch of windows and see what are the common characteristics of the output.
Okay, well, let's
Yeah.
follow up that.
One other quick question. Is there anything in the model that says I expect these peaks with to be some multiples of some period? Because after all, if it is.
No, there's nothing in the model that says that right now because you actually need to know what the period is. if you're going to do
It could be
that.
It's some
Yeah.
period, it's indeterminate, but wherever they are.
Some multiple of 2 or multiple of 3.
Something. And 4, 6, 7.
Well, there are other models for metric induction.
Okay.
Yes, there.
Because when I was looking at that,
Mhm.
I can see that there's some regularity. Not
Yes, I
necessarily,
actually
but
put the
previous-
bar lines. Yeah,
Yeah.
I put them up. Yes.
You should feel free to tell us to crank down the questions if you're going to run out of time.
Oh, when do I run out of time? Can I?
Another 10 minutes.
Another 10 minutes? Okay, yeah, that's fine. So let's go back to the example, and, whoa. Okay, all right, these are the different sections. Okay, and we want to be able to find these sections. This is the output when the window is 24/8 notes. So this is what the sections look like in the piece in color code, and these are the peaks. So there's a big peak over here where it steps up, right, a half step to crank up a notch when all the orchestra comes in. But over here, there's these local peaks for that region where it actually goes to a slightly, the relative minor, and then comes back. So this is the other, with 16/8 notes, this is how the profile changes, and this is with 12/8 notes, so smaller and smaller windows. Okay, how do these relate to musical expression? So if you were the singer, if you were the performer, and you were going to decide what you're going to do to the piece, which are all these notes you have to sing, and you have to make some expression, what would you do? Da 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 do da 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 do. You could actually go down. Da 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 do 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 da da da. Right, you can go down to make people listen, to have a more intimate sound at this point where it changes to this darker sound. Or you could actually push more, right? You can push more by doing da 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 do do do. Right, you have a few options you can do, but the thing is, you know that you can do something different at that point, and it will be very effective. Okay. So this is important to know where things and context change, and you can actually ride on that and make a difference. So that's one example. Okay, what are some problems? So these are some things I could think of this morning. There are probably more. And okay, understanding music. So hopefully you have now a better understanding of music. The time scale of groupings. At how many levels are you actually listening? You know, what are groups? How much memory do you have in order to recognize the structures? Can we find a link between harmonic and phrase structure? Is there, can we use this information to determine what are phrases? What are, where the symmetries occur when things end? And can we use this to generate reasonable and interesting interpretations of pieces? And finally, here are some resources. Most of this work is documented in papers up there in the bibliography. And this lab website and the group is under construction. And I teach a class, Engineering Approaches to Music Cognition, which has all of the course material online. So the students go through a bunch of literature, review it, and I put all the better reviews online. So. Let's see, who was first? Let's go from right to left. 1, 2, 3. Yes.
I have a question about the spiral array. So since geometric distance is sort of the modus operandi that you're using for key identification, segmentation, there's actually a free parameter, right, in the spiral array, which is basically how stretchy.
Yeah, how
is that
stretchy it
right?
is. Yeah.
So do you determine that empirically, and does it matter a lot? Or is there
No,
a
I
principle
determine
that
it
you determine?
purely mathematically, and by some usually agreed upon assumptions about, like fifths are closer than thirds, and sevenths are more distant. Diminished fifths should be really far away, and those are perceptually, yes. So you can write them into mathematical constraints, and it turns out that the one that fits all of them is square root of 2/15. So that's the aspect ratio.
Yeah, but-
Yeah.
And does that work better, do you know, than other ratios empirically?
Depends on the application you're using it for. Someone who tested this model for pitch spelling found that it really doesn't matter how much you stretch it out. But for certain applications, it actually does matter that you have that.
Thanks.
So what do you see as kind of a medium to long-term future or like what's the ultimate end in music synthesis or music co-synthesis for this work or for the field? I don't do this kind of work. I'm curious just to know what your personal vision of, are concert pianists, are those, is that a job of the past? Is there going to be a difference? No, I mean, it's a serious question.
Right. I still perform, and I still, maintain my ties to the physical aspect of actually making music. There's something about these models that isn't quite there yet. It falls far short of what humans are able to do. And part of the efforts of trying to create these models is to make the understanding of music at very high levels of music making, more accessible to people in general. Not necessarily to the experts, but the experts can use the tools, but also to just anyone who might not otherwise see the structures, for example, in the music.
So would one way of rephrasing that be to lower the bar on musical performance so that people who don't need the same amount of training to create music?
I don't know that it would actually lower the bar of traditional performance because there's the muscular aspect that needs to be developed at a certain age. But it does lower the bar for certain aspects of performance. It allows more people to experiment with different kinds of expression.
Well, you can do co-performance, right? So Max Matthews had a system
Right.
where the computer played all the notes, and all you did was add the expressive.
Add the expressive
contours.
gestures.
Yeah.
Right. Yeah. Yes.
So is the purpose, or would a side purpose of it be to discover new laws of music?
Yes.
And have you?
New laws.
In other words,
Well, this is an entirely.
Whatever you say about keys and all that pleasantness, etc. I suppose all musicians know it.
Yes, all musicians know
have you
it.
discovered something new about?
Well, this is a way of formalizing what we know. I don't think that it is new knowledge. I mean, it's what people do all the time. I mean,
But
even
is
people
this
who are not
temporary,
trained.
And eventually, if this analysis gets mature, will you discover something new? Or
Yes,
will
I
you
think
just
so. Yeah,
confirm?
it's a new way of describing music that. Well, first of all, because it's digital, we can do it in much larger volumes than before. For example, analyzing that piece, all I needed to do was spend half an hour typing it up and run it through the program, and then I had an analysis in 2 or 3 minutes. So it certainly makes, well, versus someone learning how to do it, well, there's value to learning how to do it. So I wouldn't say that it actually replaces it. I think eventually it would be one of the goals, something to work for, is to actually understand music better. So that agrees with what you're saying. Yes.
You showed us at the beginning that we were pleased when we got to a certain key, I guess back to a certain key of Phantom, and that you could segment and you could find that key with your analysis. So can you use the analysis to figure out which songs would be more pleasing than others because they return to their...
Well, it depends. Does your taste change? You know, will you like that again tomorrow or this afternoon? I think the human part of it is hard to nail down. Yeah.
This is already being done, right? There's this model. I don't remember, it's lab in Europe.
Yes, there's a company that's doing that. They're trying to
you know,
predict what's the
whether
next
something will
hit.
become a hit song or not.
Yes, but it depends what they're using. They could be
Yeah.
using people to rate things. I'm not sure entirely what the exact models are.
Well, they're using a huge array of features and just, you know,
Right,
doing
like a
training
strong
on it.
beat
It's not
versus...
clear that they actually understand the model.
Well, that's true of a lot of people doing this kind of work. So, unfortunately. Yes.
I was wondering if it was interesting watching visualizations of it searching for what would the algorithm model do with bitonal music? Does it get pulled between the two tonalities, or would it find a point in the center of those two?
Well, I don't know yet. That was something I was going to try, but because I have bitonal pieces. And you would need a different model. It needs to actually search for two to actually find those two different tonalities. Yeah. Yes?
So when you took that two-dimensional Longuet-Higgins space and you turned it into a spiral, you did the same thing that Bach did when he designed the well-conserved body, which is to collapse into equivalence classes.
Yes.
The two different, the many different instantiations
Yes,
of the note
right.
D, which have actually different frequencies if you're a very good violinist or,
Yes,
or
right.
vocalist. Right. So the question is, if we were to move away from MIDI representations of the music and actually use, sound, like the move from text to speech that we try to do here, would you be able to? What would happen? I mean, you'd like to be able to capture the fact that he's using A 440 as opposed to this A farther afield in the grid, or that A back there. Or,
Well, for violinists, that would be a difference. But for pianists, push-button instruments, that wouldn't be any different.
But I mean, am I right in thinking that in orchestral music, there would be a detectable difference?
I don't know.
More quickly determined.
I'm not sure that I could detect the difference.
I'm sure I
Yeah.
can.
So, I don't know the answer to that question. Yeah. Yes.
So, I think the big question that I have about computational music is the kinds of geometric approaches that you've been describing here are quite different from the kinds of approaches that most people in this room would think to try first.
Right.
I think most of us would say, okay, we would like to build a statistical generative grammar or graphical model of music. And I saw the phrase graphical model actually appear on one of your
Yes,
related
right.
work slides early on. And I know that
Christopher
there was work back in
Raphael,
the
yes.
70s. Maybe Steedman was in on this, but the name I think of first is Jackanoff on generative grammars of music. So do these approaches have any currency today? Have they developed further?
Yes,
how about the work
but,
in music theory that might be used to, in academic music theory, that might be used to inform the structure of such models? Not to say that you're not, in effect, being a music theorist, but your approach is different.
Quite different.
From trying to
Those
model
models
sensors.
tend to be more computationally intensive, generative grammars.
They can't be worse than what we do here, because we have a vocabulary of tens of thousands of words, and you have a vocabulary of about 12.
Well, it depends how many. Well, if you take words as sequences of notes, you really have that are of indeterminate length.
Right. So if you
Yeah.
but even if you just start with the nodes, with no chunking into with no implicit chunking into higher level units, then you should still be able to get quite a lot, because that's what you're doing, right? I mean, you're taking a windowed bag of nodes.
Right.
So it seems like a reasonable place to start. I mean, I wouldn't, what I'm saying is I wouldn't think that the computational requirements would be an objection, at least
No,
if you
no,
have the
not
kind of resources
today.
that we have
Yes,
here.
right. Yeah. No, certainly it can be tried. But I think not many people have, I don't know of, maybe I'm not current with it, but I don't know of significant efforts in that direction, making computational counterparts of these grammars. Mark Steedman actually has gone on to develop grammars for chords in jazz.
Yes.
So I think he hasn't implemented in the models in a computational way, but he has the theoretical foundations for it.
Okay, well, thank you very much.